The term black hole evokes images of a cosmic void, an object that consumes all in its path. But this metaphor belies a far more profound reality. A black hole is not merely an object, but a space-time event, a region where the four-dimensional fabric of the universe has been warped to an extreme degree. Predicted by Albert Einstein's general theory of relativity and first mathematically described by Carl Schwarzschild in 1915, these entities represent the ultimate victory of gravity over all other forces. The genesis of a black hole lies in the death of stars. When a star with a birth mass exceeding roughly 8 to 20 times that of our Sun exhausts its nuclear fuel, its core can no longer support its own weight. It collapses catastrophically, triggering a supernova explosion that blasts its outer layers into space. The remaining core continues to collapse under its own gravity. The core is crushed into a space so small that its gravitational pull becomes inescapable, creating a stellar mass black hole. A black hole is defined by two primary components. At its heart lies the singularity, a theoretical point of zero volume and infinite density where the entirety of the black hole's mass is concentrated. Surrounding the singularity is the event horizon, a one-way membrane defined by the Schwarzschild radius. At this boundary, the velocity required to escape equals the speed of light. Since nothing can travel faster than light, anything that crosses this boundary is irrevocably trapped. It causally severs a region of space-time from the rest of the universe. The experience of falling into a black hole is governed almost entirely by a single variable, its mass. Black holes are broadly categorized into stellar mass and supermassive varieties. This has a profound consequence. A stellar mass black hole has unimaginable density, while a supermassive black hole's average density can be less than that of air or water. Once an observer crosses the event horizon, the singularity is no longer a location in space, but an inevitable moment in their future. The very structure of space-time is reconfigured. The journey to a black hole's event horizon begins with witnessing the very fabric of the cosmos being twisted. The black hole's gravity acts as a powerful gravitational lens, bending the paths of photons. When a bright object lies directly behind the black hole, its light is bent around into a perfect circle known as an Einstein ring. Against this warped backdrop, the black hole itself is visible as a perfect sphere of blackness, the event horizon shadow, appearing roughly twice the size of the actual horizon. Most black holes are actively feeding on surrounding material. This matter forms a flattened, rotating structure called an accretion disk, heated to millions of degrees by friction and compression. The disk's appearance visualizes relativistic effects. The side rotating toward us appears intensely bright and blue, while the side rotating away is dimmer and redder. Light from the disk behind the black hole is bent over the top and under the bottom, creating a characteristic image where we see the far side from two directions at once. At 1.5 times the Schwarzschild radius lies the photon sphere, where gravity is so intense that photons can be trapped in unstable circular orbits, skimming the edge of the abyss. An observer positioned here would be able to see the back of their own head as light from their body completes a full circle around the black hole and returns to their eyes. At 3 Schwarzschild radii lies the innermost stable circular orbit. Any object that drifts inside cannot maintain a stable orbit and is doomed to spiral toward the event horizon, the true dynamical point of no return. The passage across the event horizon creates one of physics' most profound paradoxes. For an observer watching from a safe distance, the traveler's fall is a journey that never completes. Time flows more slowly in stronger gravitational fields. The distant observer sees the traveler's clock approaching a complete stop as it reaches the horizon. This is accompanied by extreme gravitational redshift. The traveler's image would redden, grow dimmer, and eventually fade from view as photons are stretched to infinite wavelength. From the perspective of the person falling in, the experience is starkly different. Their personal clock continues to tick at a normal rate of 1 second per second. For a sufficiently large supermassive black hole, the crossing itself is completely uneventful. There is no physical barrier, no jolt, no sensation to mark this ultimate boundary. From inside, they can still see the outside universe, though the view would be increasingly distorted and blue-shifted due to their acceleration. These divergent realities stem from the geometry of space-time itself. The basis vector in the time direction becomes progressively shorter as one approaches the black hole. The space-time interval between events must remain constant. A shorter time basis vector is compensated by a larger coordinate time interval, what the distant observer perceives as time slowing. The event horizon is thus not just a physical boundary, but an informational one. No new information from the infalling traveler can ever reach the outside universe. The true destructive power of a black hole lies in its tidal forces, the differential pull of gravity across an object. An astronaut's feet experience stronger pull than their head, creating immense stretching. The tidal acceleration is proportional to mass and object length, but inversely proportional to the cube of distance. This r-cube term means forces increase dramatically as objects get closer. This creates extreme vertical stretching and horizontal compression, eventually overcoming the electrochemical bonds holding matter together. This process has been vividly named spaghettification. The human body would be stretched into a long, thin filament and ultimately disintegrated into a stream of atoms. As tidal forces mount, they overcome the electrochemical bonds holding an object together. The human body is estimated to be pulled apart by a force of around 9,000 newtons. The point where these lethal forces are encountered depends entirely on the black hole's mass, leading to two very different scenarios. Stellar mass black holes are small and dense. With a Schwarzschild radius of only 30 kilometers, an astronaut would be torn apart hundreds of kilometers before reaching the event horizon. Supermassive black holes have enormous event horizons. Sagittarius A stars is 12 million kilometers across. An observer crossing would still be vast distances from the singularity. The tidal force at the event horizon is inversely proportional to the square of the black hole's mass. This is why, counterintuitively, bigger is safer, at least for the initial crossing. Inside the event horizon, the roles of space and time are effectively interchanged. The radial direction becomes time-like, while time becomes space-like. Moving toward the singularity is now as inevitable as moving forward in time was outside. The singularity becomes a moment in the future that one is destined to arrive at. All future-directed paths, known as worldlings, terminate at the singularity. There is no longer an outward direction in space-time. Contrary to misconceptions of total blackness, an observer inside would still see the external universe, but dramatically altered. Light becomes concentrated into a shrinking circular window. Looking ahead toward the singularity reveals only darkness, as no light can travel away from it to reach the observer's eyes. The very fabric of space-time flows inward faster than the speed of light, carrying everything with it. Any attempt to resist this flow would only hasten arrival at the final destination. The singularity is a region of infinite density and space-time curvature. For a non-rotating black hole, it's a single point. For a rotating black hole, it's predicted to be an infinitely thin ring. Even in a supermassive black hole, tidal forces grow without bound near the singularity. In the final fraction of a second, matter is torn apart at the subatomic level. The observer would never see the singularity, as it is not an object to be observed but the very end of time and space itself. The prediction of infinities signals that general relativity has been pushed beyond its domain. At these densities, quantum effects must become dominant. The true nature of a black hole's heart cannot be described without a unified theory of quantum gravity, the holy grail of modern physics. The singularity is the cosmological twin of the Big Bang. A theory that can describe the center of a black hole would likely also illuminate the origin of our universe. This hypothetical journey is a voyage to the absolute limits of scientific understanding, from observable physics to the breakdown of space-time itself. It reveals how black holes expose the limitations of our theories and point toward a deeper, more complete description of reality. The ultimate fate of an object falling into a black hole remains one of science's greatest mysteries, its answer hidden behind a perfect horizon, awaiting the dawn of new physics.